Hello viewers, welcome to DMG chemistry classes, and today I am going to talk about the solvent effects in UV visible spectroscopy. So friends, the position and the intensity of absorption bands or peaks changes with the change in the polarity of solvent. But it has been observed that the lambda maximum of non-polar compounds like conjugated dienes or other conjugated hydrocarbons remains same in polar as well as non-polar solvents. What the lambda maximum of polar compounds changes or shifts with the change in the polarity of the solvent. Okay, so today I will discuss effect of polarity of solvent on different types of transitions. But before coming on to this topic, if you have not subscribed my channel, then please subscribe and also like and share my videos. So first of all, I am discussing the effect of polarity of solvent on pi to pi star transitions. Okay, and I have told you in my previous videos that these transitions involve the excitation of a pi electron from the bonding molecular orbital to the anti-bonding pi star molecular orbital, and I have represented this transition here. So here we have a double bond, and these are the two pi electrons of a double bond. Okay, and after undergoing pi to pi star transition, one of the electron will be excited to the anti-bonding pi star molecular orbital. So here this is the representation of this transition, and in this case the excited state is more polar than the ground state, because in the ground state the two pi electrons are present in the same bonding molecular orbital and they are equally shared between these two carbon atoms. Okay, so this state or this ground state is non-polar. After the excitation of the electron, one of the pi electron has moved to the pi star anti-bonding molecular orbital, so some polarity will be developed, some positive and negative charges will be developed. Okay, and we can also explain it in a way that after the excitation of the electron from the pi bonding molecular orbital, the pi bonding molecular orbital will have a less electron, so slight positive charge will be developed, and the anti-bonding molecular orbital is having an electron after excitation, so a slight negative charge will be developed. So in this way the excited state is more polar as compared to the ground state, and this will help us in explaining the effect of a solvent. Now here I have represented it like this. So here this is the pi bonding molecular orbital, that is ground state, and pi star anti-bonding molecular orbital, which is your excited state. And this is the energy difference, that is delta E1, and this energy difference is when the sample is dissolved in non-polar solvent. Okay, so now let us discuss the effect of polarity of the solvent. As I told you that the excited state is more polar than the ground state. So if we have a polar solvent, then that polar solvent will interact more with the excited state, because let us explain. Suppose I have water as a solvent, and water is a polar solvent having slight negative charge on oxygen and positive charge on hydrogens. So definitely there will be some force of attraction between the positive and negative and the positive charges. Okay, and this is called as dipole-dipole interaction, or sometimes it could be the formation of a hydrogen bond also. Okay, so here the polar solvent will interact more with the excited state, and I have told you that any type of interaction, whether it is dipole-dipole interaction or formation of a hydrogen bond, it leads to the stability and decrease in energy. This means that due to these interaction, the excited state will be stabilized more as compared to the ground state, and the energy of the excited state will fall. So here I have represented it like this, that due to these interactions, the energy of the excited state, that is energy of pi star antibonding molecular orbital, will fall to a greater extent, whereas the energy of this ground state remains almost the same or decreases slightly. Okay, now you can see that the energy difference between the ground state and the excited state has been reduced. This means that delta E2 is less than delta E1, and energy is inversely proportional to wavelength. You know it, that is delta E is equal to hc upon lambda. So in non-polar solvent, more energy will be required and the lambda maximum will be less because energy is inversely proportional to wavelength. What in case of polar solvent, energy required for the excitation will be less. Okay, so the wavelength absorbed in this case will be longer wavelength. Smaller is the energy required, longer will be the wavelength absorbed. So I can say here that the polarity of the solvent, polarity or increase in the polarity of the solvent, that is increase in the polarity of the solvent shifts the pi to pi star transitions towards longer wavelength, and this shift is also called as bathochromic shift. This is called as bathochromic shift. Okay, so now let us represent it in the form of a spectrum. Okay, so here we have along this side we have absorbance along y-axis, and along x-axis we have the wavelength. Okay, so suppose this is the UV spectrum of any compound in a non-polar solvent, then this will be the value of lambda maximum, or this will be the value of lambda maximum. Okay, and if I have replaced or I have dissolved my sample in a polar solvent, then the lambda maximum will be shifted towards a longer value. Then we will have this type of spectrum, and this is the spectrum in non-polar solvent, and this is the spectrum in polar solvent, and I am talking about pi to pi star transition. Okay, so you can clearly see that as we have changed the solvent from non-polar to polar, the value of lambda maximum has increased. Okay, so this is the effect of polarity of the solvent on pi to pi star transition. So now let us discuss the effect of polarity of solvent on n to pi star and n to sigma star transitions. So I will replace this pi here with n. So effect of polarity on the n to pi star and n to sigma star transitions. Okay, so let us represent this transition. So here I have carbonyl group And we know that this carbonyl group is polar with the negative charge on oxygen atom and slight positive charge on carbon atom. Okay. And after the excitation of a non-bonding electron present on oxygen, okay, to the anti-bonding pi star molecular orbital, we will have, so here we have excited one of the non-bonding electron to the pi star anti-bonding molecular orbital. So you can clearly see here that after the excitation of this electron, a non-bonding electron, negative charge on the oxygen atom will decrease because one electron has moved away from it. So in this case, the oxygen atom will have a less negative charge as compared to here. Or excited state is less polar here, less polar as compared to ground state. The ground state is more polar because polarity depends upon the charges. Higher is the charges, more is the polarity. So here the excited state is less polar and the ground state is more polar. Okay, so now let us represent it further. Okay, so this is the ground state, that is non-bonding electron or non-bonding state, and here we have this pi star anti-bonding molecular orbital. Okay, and this is the energy difference between these two states, that is delta E1, and it is in non-polar solvent. Okay, now as I said that excited state is less polar and the ground state is more polar. And now I will change the solvent from non-polar to polar. Here the polar solvent will interact more with the ground state because ground state is more polar. So I have again taken water as a solvent, and negative charge is there and the positive charge is as I explained earlier, and there will be a dipole-dipole interaction, or hydrogen bond can also be formed here between your oxygen atom and the hydrogen of the water molecule. Okay, so here the interaction will be more between the ground state and the polar solvent because ground state is more polar. And as I said that any type of interaction, whether it is dipole-dipole or hydrogen bonding, it leads to stability and decrease in energy. So due to these interaction here, the ground state will fall in energy. That is, the energy of the ground state will decrease more to like this. So this is now N and this is our ground state. Okay, and the energy of this excited state will not fall by a significant amount because the excited state is less polar. So the interactions will be less. So this is our pi star. And now this energy difference is delta E2. So this is energy difference when we have polar solvent. Okay, now you can clearly see here that in the polar solvent, or due to these interactions, the energy difference between the ground state and the excited state has increased. That is, this delta E2 is greater than delta E1. So delta E1 is less. So here, as I explained, less energy, a longer wavelength will be absorbed. But here in polar solvent, large amount of energy will be required for the excitation. So here a shorter wavelength will be absorbed because energy is inversely proportional to wavelength. So now I can say, or I can conclude, that polarity or increase in the polarity of the solvent increase in the polarity of the solvent will shift N to pi star transitions towards shorter wavelength. Okay, shorter wavelength, and this is also called as hypsochromic shift. Hypsochromic shift. And the effect of polarity of the solvent on N to sigma star transitions will be same, because in this case also a non-bonding electron will be excited to the sigma star anti-bonding molecular orbital. Okay, and this non-bonding electron will always be present on some heteroatom like your oxygen or nitrogen or halogens or sulfur. So when this non-bonding electron is excited to the anti-bonding orbital, definitely the negative charge on the heteroatom will fall, and in this case also the ground state will be more polar than the excited state, and the effect will be the same as I explained in the case of N to pi star transition. So I can say that the increase in the polarity of the solvent will shift the N to sigma star transitions towards the shorter wavelength. So effect is same in both type of transitions. Okay, so this is all about the solvent effects in UV visible spectroscopy, and in my next video I am going to take up the concept of chromophore and oxochrome. So keep watching my videos, like and share my videos, and subscribe my channel. Thank you very much.